Testing. Hello. Things are working. Hi, Coffee. Hi, Mima. Hi. What's up? I I pressed start streaming, and the internet gave up on me for like a second, and then like way too many issues just happened. Uh, um, I am doing well, and mostly my problems with streaming is to do with my sleep. Otherwise, everything is good. Thank you for asking. I yeah, I'm gonna be like that person and be like, oh my god, I haven't done this in a long time. I don't even remember how to do this. I'm kidding. Um, well, we made it. I was thinking today's stream is probably going to be a short one. So yeah, maybe 1 hour. We'll see. What is up on you guys' side? How's life going? Let's see if okay, we are sharing the screen correctly. Yay, we did it. Okay. Okay. So I think I'm gonna go for this one today because I've left it for too long, and when you leave something for too long, surprise, surprise, you're not gonna make progress. So let's do that. Oh, I forgot to charge my laptop. It will survive. Oh well, it's fine. Let me know if you've learned anything cool recently. Oh, not doing well. Have 3 projects to do. Oof. I mean, isn't it right now very late for you? Like, you have to sleep sort of late. um, are you going to work, quote unquote, tomorrow, which is today, basically? Because if so, you really need to rest. Projects, probably. Good luck. Good luck. Inshallah, you'll get there. Just when like you're in the trenches, you're in the deep. You're like, there will be I don't know how to say this, but like it will be all right at the end, something like that. I believe in that most of the times, like almost 100% of the times, I believe that things will be okay. So yeah, okay. How about resting your eyes, just for a bit? And if you'd like, I'll be in the background, or you can listen to something nicer. So apparently today I'm going to be learning about fast tokenizers, which difference is that one is made in Rust, one is made with C. Okay. Fast tokenizers, special powers. In this section, we will take a closer look at the capabilities of tokenizers in transformers. Up to now, we have only used them to tokenize inputs or decode IDs back into text, but tokenizers, especially those backed by the HuggingFace tokenizers library, can do a lot more. To illustrate these additional features, we will explore how to reproduce the results of the token classification, NER recognizer, named entity, okay, and question answering pipeline that we first encountered in chapter 1. Okay, play video, check for sound. Oh, did not fix sound.
Why are fast tokenizers called fast? In this video, we'll see exactly how much faster the so-called fast tokenizers are compared to their slow counterparts. For this benchmark, we'll use the Glue MNLI dataset, which contains 432,000 pairs of text. We'll see how long it takes for the fast and slow versions of a BERT tokenizer to process them all. We define our fast and slow tokenizer using the Auto Tokenizer API. The fast tokenizer is the default when available.
Okay, adjusted volume, fixed some stuff, sorry about that. So the difference between fast tokenizers and normal tokenizers is that one is fast and one is not, because that's a really long post if that's the only difference. Hoping that's not the case. Could be though.
So we pass along useFast equal false to define the slow one. In a notebook, we can time the execution of a cell with a time magic command like this. Processing the whole dataset is 4 times faster with a fast tokenizer. That's quicker indeed, but not very impressive. This is because we pass along the text to the tokenizer one at a time. This is a common mistake to do with fast tokenizers, which are backed by Rust, and thus able to parallelize the tokenizations of multiple texts. Passing them only one text at a time is like sending a cargo ship between 2 continents with just one container. It's very inefficient. To unleash the full speed of our fast tokenizers, we need to send them batches of texts, which we can do with the batch equal true argument of the map method. Now those are impressive results. The fast tokenizers takes 12 seconds to process a dataset that takes 4 minutes to the slow tokenizer.
Whoa.
Summarizing the results in this table, you can see why we have called those tokenizers fast. And this is only for tokenizing text. If you ever need to train a new tokenizer, they do this very quickly too.
Cool. Oh. By the way, I don't know if anyone uses it, but there's a plugin, extension, Chrome extension, that removes suggested videos, end card videos. He's probably French, yeah. HuggingFace is a French company, I think, or at least the founders are French. So like, if they recruit local talent, then they are most likely French. But I know they have a lot of people from all over the world, so I am not, okay, yeah. I am not a very informed about their employee. Yeah. Oh, wow, that's really cool. Wow. Yeah. They are probably really cool people. I know of them, so. In the following discussion, we will often make the distinction between slow and fast tokenizers. Slow tokenizers are those written in Python inside the transformers library, while the fast versions are the ones provided by the tokenizers library, which are written in Rust. If you remember the table from chapter 5, not really, that reported how long it took fast and slow tokenizer to take the drug review data set, you should have an idea of why we call them fast and slow. Sort of remember the batch thing? I mean, here the difference is not that much. Oh, whoa, my brain just woke up. Difference is 10 seconds to 4 minutes, or 1 minute to 5 minutes. I see. When tokenizing a single sentence, you won't always see a difference in speed between the slow and fast versions of the same tokenizer. In fact, the fast version might actually be slower. Right, because it's a single sentence. Only when tokenizing a lot of text in parallel at the same time, you will be able to clearly see the difference.
The fast tokenizers of the transformers library are fast, but they also implement features that will be super useful for data pre-processing and post-processing. Let's have a look at them. First, let's have a look at the usual output of a tokenizer. We get input IDs that correspond to token, but we lose a lot of information in the process. For instance, here the tokenization is the same for the two sentences, even if one has several more spaces than the other. Just having the input IDs is thus not enough if we want to match some tokens with a span of text, something we'll need to do when tackling question answering, for instance. It's also difficult to know when two tokens belong to the same word or not. It looks easy when you just look at the output of a BERT tokenizer, where we just need to look for the dash dash, but other tokenizers have different ways to tokenize part of words. For instance, Roberta adds this special G symbol to mark the tokens at the beginning of a word, and T5 uses this special underscore symbol for the same purpose. Thankfully, the fast tokenizer keeps track of the word each token comes from, with the word IDs method you can use on the outputs. The output is not necessarily clear, but assembled together in a nice table like this, we can look at the word position for each token. Even better, the fast tokenizers keep track of the span of characters each token comes from, and we can get them when calling it on one or several texts by adding the return of set mappings equal true argument. In this instance, we can see how we jump positions between the --s token and the super token, because of the multiple spaces in the initial sentence. To enable this, the fast tokenizers store additional information at each step of their internal pipeline. But the internal pipeline consists of normalization, where we apply some cleaning to the text, like lowercasing or removing the accents, pre-tokenization, which is where we split the text into words. Then we apply the model of the tokenizer, which is where the words are split into tokens, before finally doing the post-processing, where special tokens are added. From the beginning to the end of the pipeline, the tokenizer keeps track of each span of text that corresponds to each word, then each token. We will see how useful it is when we tackle the following tasks. When doing masked language modeling, one variation that gets state-of-the-art results is to mask all the tokens of a given word instead of randomly chosen words. This will require us to use the word IDs we saw. When doing token classification, we'll need to convert the labels we have on words to labels on each tokens. As for the offset mappings, it will be super useful when we need to convert token positions in a sentence into a span of text, which we'll need to know when we're looking at question answering or when grouping the tokens corresponding to the same entity in token classification. To have a look at these tasks, check the videos linked below.
Okay, I shall if I get there. Why does it become small each time I leave the video? Okay. The output of the tokenizer isn't a simple Python dictionary. What we get is actually a special batch encoding object. It's a subclass of a dictionary, which is why we were able to index that into that result without any problems before, but with additional methods that are mostly used by fast tokenizers. Besides their parallelization capabilities, the key functionality of the fast tokenizer is that they always keep track of the original span of text. The final tokens come from a feature called we called offset mapping. This in turn unlocks features like mapping each word to the tokens it generated or mapping each character of the original text to the token it's inside. We want to do mass modeling, say for all tokens that make up the name to be US presidents. I thought it was like, what is what is us presidents? Who's the president? That's fine. All tokens that make up the name to be masked, not okay, got it. Now I understand what you mean. because their names are multiple parts. Yeah, but because of the thing, the presidential debate, that's right there. It's on everybody's mind. Unlocks features like mapping each word to the token it's generated, or mapping each character of the original text to the token it's inside, and vice versa. I shouldn't read so fast. My brain can't even process. Let's take a look at an example from Transform. Oh, yeah, okay, that's code. I don't need to read this. Anyway, so I think this is not this. Okay. I'm gonna close this. I need to get myself fast tokenizer. I need a compiler, I think. Okay, so sorry. Thanks. Okay. So what we're saying is getting birth base cased, and then tokenizing this and looking at the what type, what is the output, which we said is called a batch encoding. Is that the case for every Transformers tokenizer? Ooh, is it fast? Cool. You can ask it if it's fast or not. What else? Yes, as we mentioned, we get a batch encoding object. Since the auto tokenizer class picks a fast tokenizer by default, we can use the additional methods the object has. For example, there are two ways to check if it's a fast or a slow one. One is you ask the tokenizer if it's fast, or you ask the encoding, let's see what a fast tokenizer enables us to do. First, we can access a token without having to convert the IDs back to tokens. I don't remember how we used it before, sadly. I think that's not a good thing. But, like, if I say encoding, will you just give me information about the type? You give me everything. But, if I say tokens, you give me the actual value of the input IDs. Now that I like. Nice. Oh, okay. All right. We have the sentence. In this case, the token at index 5, that's all S. Part of the word Sylvian in the original sentence. Oh, wow. What happened? Why is it separated like this? Hello. Hi. TT? That's a cool name. We can also use the word IDs. Word IDs? We don't have them here. So just the index for the Ah, okay, so you have 3333, which means the Sylvian name was split into 4 parts. Is that a good thing? I don't see that as a good thing. I see that as a bad thing. We can see that the tokenizer special tokens, separator, and I forgot what this stood for, but I'm sure my brain can think about it later if it's needed, are mapped to none because they're not words. Okay. And then each token is mapped to the word it originates from. This is especially useful to determine if a token is at the start of a word or if 2 tokens are in the same word. I agree. That is very useful. We could rely on the, what is that? Why does the hashtag look like a really weird road? Prefix, but it only works for because each tokenizer has their own way of each tokenizer has their own way to format it. Yeah, this method works for any type of tokenizer as long as it's a fast one. In the next chapter, we'll see how we can use this capability to apply the labels we have for each word properly to the tokens in tasks like named entity recognition and party speech tagging. We can also use it to mask all tokens coming from the same word in masked language modeling, a technique called whole word masking. Got it. That does help. Okay. The notion of what a word is. Huh? I think N is missing. Of what a word is complicated. For instance, does I'll contraction of I will count as 1 or 2 words? It actually depends on the tokenizer and the pre-tokenization operations it applies. Some tokenizers are split on space, so they consider it as 1 word. Others use punctuation on top of spaces, so we'll consider 2 words. See the difference between them? Checkpoint, Tokenize, what is 81s? Just 81s, that's it. What do I observe? We have Roberta base. Let me try. Oh. Do I need to run these? Oh wow, that's so cool. Put start to end and you can have the name back together. That's pretty cool. I want to try the Roberta. We have this case. We have tokenizer. I'm going to call the other one tokenizer 2. And then we can have encoding 1 and encoding 2. That should be example 2. We actually need 1 example for both, obviously, because we're testing them. And then we can, print both of them. Print encoding 1, and then print number 2. And apparently I'm supposed to do 80. I'm going to do 80s. What's the difference between 81s and 80s? Okay, or 90s. There's a dot. Do I need the dot? Let's say I'll be enjoying the 80s. What is good with the 80s? Sorry, I don't do anything 80s. This 90s game, whatever. Okay, there we go. So we have the al and the numbers with a s, and I need to update this to become tokenizer 2 Roberta instead of Bert, and then we run. Any designers would be more common probably than 81s. That's, yeah, like, yeah. Oh, I'm supposed to do the tokens. Give me the tokens. Well, tokens. How was I supposed to write it? Tokens. Token with an S. And then tokens. And then we take you out. We try it. Okay, so we have this is 3 parts. This here is 2. And then 90s with the 90s. Yeah. Roberta is different. I think y'all can see it now. And even the start of sentence and end of sentence is also different. Cool. We did it. Okay, next. Similarly, there's a sentence IDs method that we can, the thing with the, what's the difference between sentence IDs? We have word IDs. We also have sentence IDs. We can use to map a token to the sentence it came from, though in this case, the token type IDs returned by the tokenizer can give us the same information. All right, lastly, we can map any word or token to characters in the original text and vice versa via the word to chars, or token to, should I read it as chars or cars? Because character, but here it feels like chars. Help me. I'll go cars, it's okay. And the cars to word or, okay, so we have word to character, I'm guessing. And then token to character, character to word, character to token. Both ways, got it. Methods, for instance, the word IDs method told us that ly is part of a word at index 3, but which word is it in a sentence? We can find it out like this. So we get the index from start to finish, and then you put it together with the range, and then you make it. As we mentioned previously, this is all powered by the fact that the fast tokenizer keeps track of the span of text each token comes from in a list of offsets. To illustrate their use, next we'll show you how to replicate the results of the token classification pipeline manually. All right. Create your own example text and see if you can understand which tokens are associated with word ID, and also how to extract the character spans for single word. For bonus points, try 2 sentences. Nah, not feeling it. But do I have anything that was botched in my test? The only thing that's somewhat separated is the I could do something about that, but that's as far as I'm feeling. That my generosity goes that far. 1 and 2 and 2 Yes, 2. And go. We put, oh, what? Wow. So this is separated, but these two are together. Okay, interesting. I thought you'd... did we have the word IDs? Is that what it was? It was word IDs, okay. So encoding 2, show me your word IDs. But if this is number 1, word IDs. Huh? So they're all different. Or was it encoding number 1? Oh, my mistake. It was supposed to be encoding number 1. No. Yes. Yes. Nope. Nope. Cool. So everybody's like, we're good. Encoding 2 and 1. Two, 1. What am I even fighting for? Okay. We don't need to put anything back together. Okay. Not a hill I'm willing to die on. Inside the token classification pipeline, in chapter 1, we got our first taste of applying near... Why am I reading as near? This isn't Death Note. Okay. Named entity recognition. Where the task is to identify which part of the text corresponds to entities like persons, locations, or organizations. Persons, locations, or organizations. With the transformers pipeline function. Then in chapter 2, we saw how a pipeline groups together the 3 stages necessary to get the predictions from a raw text, tokenization, passing the input through the model, and post-processing. The first 2 steps in the token classification pipeline are the same as in any other pipeline, but post-processing is a bit more complex. All right, we start from the top.
Let's have a look inside the token classification pipeline. In the pipeline video, we looked at the different applications the Transformers library supports out of the box, one of them being token classification. For instance, predicting for each word in a sentence whether they correspond to a person, an organization, or location. We can even group together the tokens corresponding to the same entity, for instance all the tokens that form the word Sylvain here, or HuggingFace. The token classification pipeline works the same way as the text classification pipeline we studied in the previous video. There are 3 steps: the tokenization, the model, and the post-processing. The first 2 steps are identical to the text classification pipeline, except we use an auto-token classification model instead of a sequence classification one. We tokenize our text, then feed it to the model. Instead of getting 1 number for each possible label for the whole sentence, we get 1 number for each of the possible 9 labels for every token in the sentence, here 19. Like all the other models of the Transformers library, our model outputs logits, which we need to turn into predictions by using a softmax. We also get the predicted label for each token by taking the maximum prediction. Since the softmax function preserves the orders, we could have done it on the logits if we had no need of the predictions. The model config contains the label mapping in its ID2label field. Using it, we can map every token to its corresponding label. The label O corresponds to no entity, which is why we didn't see it in our results in the first slide. On top of the label and the probability, those results included the start and end character in the sentence. We'll need to use the state mapping of the tokenizer to get those. Look at the video linked below if you don't know about them already. Then, looping through each token that has a label distinct from O, we can build the list of results we got with our first pipeline. The last step is to group together tokens that correspond to the same entity. This is why we had 2 labels for each type of entity, I pair and B pair, for instance. It allows us to know if a token is in the same entity as the previous one. Note that there are two ways of labeling used for token classification. One, in pink here, uses the B-bear label at the beginning of each new entity, but the other, in blue, only uses it to separate two adjacent entities of the same type. In both cases, we can flag a new entity each time we see a new label appearing, either with the I or B prefix. Then take all the following tokens labeled the same with an I flag. This.
Hello. Hi, Liz K. Thank you. I hope you have a nice day as well. I really like how this looks. I'm going to check the inference in a bit.
Coupled with the offset mapping to get the start and end characters, allows us to get the span of text for each entity.
Cool. Can we go and check inference? Oh, how pretty is that? Whoa. There is no model card, but this is based on... It's not based on anything. Someone just worked on it. This is location. If we update it, I work at, let's say NASA. We're feeling NASA today. And I live, you can't live in London if you work for NASA. You have to work for ESA. So let's make it ESA. It's with an E, right? Yes, European Space Agency. You better work. Hey, ESA is an organization. That's pretty. What else can we, what other stuff can we do? Where's the table with the I in the... Show me.
We can build the list of results.
We have location, miscellaneous, that's it. Organization, location, and person. Oh, we got all of them. I'm not feeling miscellaneous. I hope to visit the ISS one day. Don't know if ESA works with the ISS though. Yep. ISS is not really an organization. It's technically a location, so... Right? Gotcha. Okay, getting the base results with pipeline. Let's grab a token classification pipeline so we can get some results to compare manually. Model used by default is this one that does named entity recognition on sentences. Ooh, is that the output for each entity? Cool. I'm gonna test my own sentence. Simple version, not simple version. Got it. Let me get my Sarah sentence and try for that. Should I go simple version or should I go not simple version? I think simple version is okay. I just want to see how sure it is that the ISS is... Oof. Cool. Nice. How sure it is that the ISS is a location or an organization. You do that, and then we're gonna do this here. Why does it look less pretty? I want it... yeah, I know. Can you make it more pretty? Should I read this? Go. 99. Whoa, 99%. Everything is 99. Well, at least it's less sure than it is with these ones. But like, that's not. Is International Space Station an organization? Like, do I have to Google this? This is taking me. Oh. Whoa, we have a 3D version. I'm gonna test that later. Pretty. Oh, okay. He says also worked on it. That's cool. But like, it's an artificial satellite, and technically the moon is also a satellite. So satellites can be locations. There. I have decided. The model properly identified each token generated by Sylvian as a person. Yes. The thing that it's less sure about is, ooh, the HuggingFace one. Ah. It's like, is the word face an organization? We can't be sure. Each token generated by HuggingFace as an organization and token Brooklyn as a location. We can also ask the pipeline to group together. Okay, haha, that's cool. Once in a lifetime, I get subscription notification from YouTube, which is pretty cool. Thanks. Thank you for that. Okay. Yep. I should not get distracted, but I am. I have this like 1 second, 6 seconds of me trying to stream. I need to unlist that or maybe even delete it later. Okay. So pipeline. Ooh, the name was Gypsy Girl. Whoa, that's a cool name. I mean, I don't know if the word is in use anymore, but it's still a cool name. Ask the pipeline to group together the tokens that correspond to the same entity. We can do that? Oh, that's what's the difference. You group them. Ooh, that's pretty cool. And maybe you average out? Yeah, probably the score. That's cool. All right. The aggregation strategy picked will change the score computed for each group entity with simple scores, just the mean of the scores of each token in the given entity. For instance, the score of Sylvian is the mean of the scores we saw in the other example. Got it. First, other strategies are also available. So we chose simple. We can do first, max, or average. That makes sense. Where the score of each entity is the scores of the first token, or is the highest, or it's the average. For HuggingFace, yeah, there would be no difference with the simple strategy, but HuggingFace would have, for Sylvian, but for the HuggingFace 98, the average of hugging and face. Okay, let's see how we can obtain these results without using the pipeline function. Why do you think finite? Why? From inputs to predictions. Yes. So, using the checkpoint that we said we would use, okay. Still calling it as from pre-trained. Let me read this first. First, we need to tokenize our input and pass it through the model, which is what we had done in chapter 2. We instantiate the tokenizer and the model using the auto ... classes and use them. Okay, so we have the tokenizer, we have the model, which is token classification, and then we give the example to the tokenizer, and then we give it to the model. That's it. And for the output is something that we have to work with, right? Since we're using the auto model for token classification, here we get one set of logits for each token in the input sequence. Cool. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't really count it that way, can we? I think we can't. Oh, it does say 9. Huh, that's nice. Actually, we can. Cool, cool. We have a batch with one sentence of 19 tokens, and the model has 9 different labels, so the output of the model has a shape of 1 by 19 by 9. Like for the text classification pipeline, we use a softmax function to convert those logits to probabilities, and we take the argmax to get predictions. Note that we can take the argmax because softmax. Okay, my brain did not work. For the text classification pipeline, we use a softmax function to convert logits to probabilities, and we take the argmax to get predictions. Note that we can take the argmax on logits because the softmax does not change the order, which is a good thing. Got it. Okay. Okay, so here we do softmax, logits of the dimension -1. I'm not sure what we mean by that, but okay. And then we get probabilities, which is, I guess, the 0th thing, index. And then we go predictions, output, logit, argmax, and then we get predictions. Do we do anything with probabilities? Are these predictions for 0? Oh, these are the thing with the thing with the in the video, the 4 and the 8 and the right. That was that scared me just a bit. Nice. Aha. And then the ID to label thing, if we look at it, I didn't have to run that. 4 is a person, 6 is an organization, and 8 is a location. We had B and I because I forgot. You're gonna tell me? Beginning or inside? Cool. As we saw earlier, there are 9 labels. Oh, so these labels are for that. 19 tokens, 9 labels. All right, I thought it was my 9 count. -1 meaning the last dimension. It's supposed to mean the last thing when it comes to index. I guess, sure. Probably. 0 is the label for the tokens that are not named entity. Stands for outside. Huh. I read it as 0, but that's actually O. And we then have 2 labels for each type of entity: miscellaneous, person, organization, and location. What does count as miscellaneous? I'd like to know. The label B dash indicates the token is at the beginning of an entity, and I indicates it's inside. For instance, the current example we have is the name. Well, it's all 4, so it's all I don't see a 3. Aren't I supposed to see a 3? E, like this. Like a B, I, instead of an I, all the way. Alice and Bob. Oh, isn't that wrong? Yeah, that's what I'm thinking. Thank you for validating my opinion. You might think the model was wrong in this case, as it gave I to all 4 tokens, but it's not entirely true. There are actually 2 formats for the, we have IOB1 and IOB2. In pink below, I'm using dark mode, is the one we introduced. Okay. The label B are only ever used to separate 2 adjacent entities of the same type. Aha, makes sense. That sort of makes sense. The model was using what the model was using was fine-tuned on the dataset using that format, which is why it assigned. Okay. I mean, if you know the format, then it shouldn't really matter. Oh, hi, JSS, what's up? Yep, I saw your name and now I'm thinking about the ISS again. It's going to die really soon. I think 2030, right? Or was it? It's 2030, right? It's not like super soon. It was in the news. With who gets to shoot it down. I mean, not shoot it down. Bring it down? I don't know. Will they drop it? Will they let it go to dark space? I did not check. With this map, you are ready to reproduce almost entirely the result of the first pipeline. We can just grab the score and label of each token. That was not classified as 0. Our output looked like this, right? So all I have to do is make it look pretty. Bring the text, bring its prediction based on index, and bring its label. Yeah? So we have a loop on the predictions. We say ID to label based on prediction. And if it's not 0, make it look like this. Label, score, ID, and prediction. Okay, so that's why we needed probabilities. I thought, And then token with the index. And that's what it looks like. That's the not simple version. We could do simple version, but I don't have the energy to do that. It's like as if I'm writing the code. Transformers are beginning to be burned into silicone. Yeah? Huh. That is probably... Now I'm thinking about silicone-based life. Isn't that what the episode of Cosmos was about? My brain just like went opposite direction of what you were saying. But like models, I also like heard somewhere that you can store data on organic matter. So just you saying that is probably possible. Yeah. Why not? And what is organic matter? Everything is organic, technically. Just like how people say, that's chemicals. Yeah, everything is chemicals. Okay. This is similar to what we had before. True. With one exception, pipeline also gave us information about start and end of each entity in the original sentence. Did it? Organic AI bots. Kill them with fire. This is where offset might come into play. To get offsets, we just have to set return offset to true. Where? Oh, when we do the tokenization? That's cool. Organic as in pesticide free, or as in the chemistry has carbon in the molecules. Maybe, probably that thing with the carbon in the molecules. Probably. Like, maybe from somehow something with the word alive, I don't know. I might be using that word incorrectly. So each tuple is the span of the text corresponding to each token. Okay, where 00 is reserved for the special token 00 from the beginning and 00 at the end. We saw before that token with the ID 5. Oh, at index 5. 1, 2, 3, 4, 5. Huh? Oh, sorry, not you. 1, 2, 3, 4, 5. 12 to 14. If we grab the corresponding slice in our example, we get the YL. All right. Program to repair organs. Oh, so that's different, right? Because that's like teaching a robot how to do surgery, I guess. We went from doing a surgery on a grape to I don't know. I don't think we're at, I mean, I don't know if that's what you mean, but I don't know, we're at a point that I don't think that would be safe. Nope, from stem cells. Cool. I mean, oh, sorry, I did not see that message at the top. Yeah, I mean, stem cells, yeah. Those are, that's like the sandbox to test with, right? Using this, we can complete the previous result. So our result was, I want to do it on, we have the Sylvian one. Does this work here? No, sorry. Okay. Does this work here? No. Because it's not in a loop? No? Yes. Can I put it in a loop? How would that look? Oh, it will look like, yeah, it will fill itself up. Got it. Because it's appending. Let's not, do we need results? I don't think we need the results. I'm just gonna print. How would that look? All right. My bad. I think like stem cells are cells in the body that can become other cells based on where they find themselves, as opposed to most cells that are made to do a specific thing. In my head, stem cells are stuff they do in labs. So programmed AI stem cells. Whoa, that is cool. But yeah. Okay. Wow. Yes, stem cells. Don't have enough information, but yeah. There. I can't think of an equivalent. Ooh, actively do repairing. That is really cool. Is there like an article about that you can share? That seems really cool. Are we actually turning ourselves into lizards? The joke is that lizards do that. Stem cells aren't in the body, just get studied in labs due to their properties. Yeah. Okay, I see. Got it. Thank you. These are the offsets, right? And then what do we do with the offsets? So we have the list of offsets, and we say, give me the start and end, and we can have start and end. That looks nice. Why does my result look weird when their result looks pretty? Fine, I'll update this one as well. How would this be? Probably errorness. Probably give me an error. No, did not give me an error. Nice. Their in-body is doing many things currently. Yes. Start and end. Nice. Which example should we take? 12 to 18. We can do that. 12 through 18 should be the guy's name. Oh no, it was supposed to be, forgot 11. I forgot 11. It's on. Nice. So, grouping entities, all right. Using the offset to determine the start and end keys for each entity is handy, but that information isn't strictly necessary. I mean, my question is that why is the guy's name separated into funny parts, and why is, like, shouldn't be the case, even though it recognizes it as one thing. So tokenization is the issue, not the named entity recognition here. When we want to group the entities together, however, the offset will save us a lot of messy code. For example, if we want to group together tokens HuggingFace, we make special rules that say the two should be attached while removing the hash, okay. And the face should be added with a space. Yeah. Why though? In my brain, HuggingFace is a one word, but that would only work for this particular type of tokenizer. Yes. Why do I feel like NLP study is fairly moot? I do not know what you mean by moot. Don't know what that means, sorry. We would have to write another set of rules for sentence piece, or, oh yeah, byte pair encoding tokenizer discussed later in this chapter. Let's do that, please, because I've seen them. I don't know how they work. With the offsets, all that custom code goes away. We can just take the span in the original text that begins with the first token and ends with the last. So in our case, we can put it back together. Got it. Counterproductive. Don't think I've heard moot. Is it moot? It doesn't feel counterproductive to me. I don't know. I just want to understand what's happening in the world, and or be able to do something that I want to do. You know, like if I want to make something, then hopefully through this I can understand things better. Like I am moot point becomes pointless. like I try to do things on my own practically, less on stream, and understanding stuff that's out there is one of my goals, so it doesn't feel pointless for me. Write the code that post processes like predictions. Post processes the prediction while grouping entities. We will group together entities that are consecutive and labeled. Oh, yeah, we saw that code in the video. Okay, except for the one that's O, right? Which O, huh? Yes, it could be I or B, but I thought there was a formatting. We stop grouping an entity when we get to 0 or O or whatever. Or B. Are we using that formatting? We have the offsets, we have the tokens, input with offset, offset by itself. Uh-oh. Big lag. Currently, it's okay. Like, compared to the other day, internet is pretty okay. So, looping through our predictions while ID is less than, oh, wow, we're updating ID. Less than length of predictions. Okay, you felt like using a while. That's, someone should clap for that. We have our prediction, we have our label with the label to ID. If it's not O, remove the first two things. We have a start. Isn't that supposed to be the end? Do we not care? And then grab all tokens with the I. This is cool. Ooh. Are we? Oh, we're making the simple version. Now I understand what we're doing. Because then we are currently doing the mean, and then we're putting the word together. What were we doing here? Ah, the score. Ah. Oh. We get the same result as the simple pipeline. Cool. Wow. Another example of a task where these offsets are extremely useful is question answering. Diving. Not driving, we're diving. Water, not land. Into that pipeline, which we'll do in the next section. Will also enable us to take a look at one last feature of the tokenizer in the transformers library, leading with overflow tokens when we truncate an input to a given length. Okay. Brain is overheating, but I'm gonna probably pause here. So we looked at fast tokenizers with the object, the things that it has. Cool. All right, we have a long way to go. I'm just looking at what's left, and I might have not so recently watched Mulan, so yeah, we have a long way to go. Okay. Yeah, I mean, all right, so today we learned about how to use fast tokenizers, I guess. and the offsets and the indexes and all of that. That was pretty cool. I was able, of course, I was able to what are the best LLMs out there? I actually like the GPT's part of ChatGPT because they're more focused on stuff. What was I saying? Yes, it's been over an hour, which is cool. And I said I will end the stream. In 3 minutes, I'm like, okay, stream end. So we'll do that. Thanks for being here. Thanks for the conversation. And if in any way you find that I'm not providing value, I do not mind if you do not watch it. I'm doing this for myself. Oh yeah, Claude that's true. Is it available for use? Actually, there's a probability of stream tomorrow. We'll see. We'll see how it goes. Because Sunday we had internet. Yeah. In my brain, I thought we didn't, but then we did. And I was not mentally prepared. Yeah. Because, I have this, schedule in my brain. And if there is not that thing in my brain, then I'm not prepared to do it, even if I can. So we'll see. We'll see if I am going to prepare my brain as if there's a stream tomorrow. And if it's not, then cool. No worries. So thanks for being here. Thanks for the conversation, and see you next time, where we'll probably be looking at the tokenizers more, and maybe some of the lecture. Depends. If I have the same amount of time or less or more, we'll see. Yeah, I had the same question about Claude. I don't know if it's maybe you use it with APIs. I don't know. Okay. The stream will be ending. If there's anything else, let me know. Otherwise, I am out of here because I have a long day ahead of me. Maybe not too long, but we'll see. We shall see. Cool. That's pretty cool. That's pretty cool. No research. I saw some tables that compare ChatGPT was it 4.5 with Claude? Ooh, cool. Free version, but they might cap, obviously. Yeah. Yep. Products have caps, which is normal. GP 4.0. Yeah, something. It has a name, yes. Okay. Cool. Yeah, I mean, they're really useful. I don't know. Is it at the point of figuring things out? They are more intuitive because you can ask them humanly compared to how useless Google has become. Paid is also capped. I mean, yeah, they have to cap it somewhere. I mean, you can cap it at thousands. I don't know. Is that a lot? I don't know. Whatever. Many paid accounts. Life in a subscription-based world. Oh well. What sort of superpowers? Can they help you fly or something? Okay. I will be heading out, if that's all right. See you next time. Ooh, nice. But only the US got to see Google with AI recommending. I haven't seen it. Yeah, very useful stuff. The rest of us see it. Yeah, people. Yeah, complaining about it. True. The rest of us see it on Reddit and Twitter. Cool. It's cool that it helps you make your work faster. But if you are working for a boss, be careful. Don't make your work too fast because they will expect more always. Okay. I will be trying to end the stream, and thank you for the conversation. I would prefer to stay, but I can't. So, yeah. There's never used it. Oh, we're talking about Google issues, not Claude. Google had issues with the AI, their Bard/Gemini recommendation when doing Google search. It's pretty funny, actually. Yes. Okay. Now, yeah. Thank you. Inshallah, we'll learn more together. Yeah. Useful stuff, hopefully. Otherwise, you probably can learn by yourself. All right. I'm gonna head out. Gonna end the stream with a countdown of 5. Okay. Cool. Yeah. Google it. So 5, 4, 3, 2, and 1. See you next time.